This video gives a grand overview of Chapter 6, which is about neural networks. Computers are better than humans at playing chess, Go, poker, Dota, or StarCraft. They compose pop songs, write fiction stories, draw paintings, replace actors in movies, and drive vehicles. Whenever a computer does something mind-boggling, you can bet that a neural network is involved. We start out with a video that explains the basics of neural networks. What is a neuron? Why are neurons connected in layers? How do we compute a function with a neural network? And what are the different activation functions? In contrast to the script, the video uses an explicit bias term. The script, on the other hand, includes the bias term in the weight vector. Next is a video about gradient descent, a topic that we already know from Chapter 5. This video presents the topic slightly differently, and more tailored to neural networks. Video number 3 presents the backpropagation algorithm, and how stochastic gradient descent is applied to all the layers in a neural network, using an intuitive walkthrough example. The video teaches the intuition of the backpropagation algorithm in an easily accessible way. The next video then explains all the essential math of backpropagation and stochastic gradient descent. How do we compute the relevant derivatives, and how are the weights updated? But do neural networks have limitations, or can they compute anything? Indeed, in principle, neural networks can approximate any function. The main tool is the universal approximation theorem, which states that any continuous function can be approximated arbitrarily well with a neural network. The video shows the proof of the universal approximation theorem with an example function. The proof is constructive, in the sense that we actually create a small neural network with a single hidden layer. Together, these 5 videos cover all the basics of neural networks. However, real neural networks use a series of techniques to speed up the learning process. We review some of the most important techniques in the next few videos. First, we start off with convolutional neural networks, or CNNs. Convolution is a neural network layer that works on spatial input data such as images. A CNN applies the same function, the same weights, to all neighborhoods of the input layer, with the idea that an object is still the same object no matter whether it is located rather on the left or the right side of an image. So instead of having to train a large number of weights for a general-purpose neural network, we train much less weights of a convolution filter. Having fewer weights substantially improves the learning process. CNNs were the first neural networks producing astonishing results. The idea of weight sharing can also be applied to time-based data. This is what recurrent neural networks do. Given a temporal signal, recurrent neural networks will repeatedly apply the same trained filter. As a result, recurrent neural networks can deal with a time-based signal with few weights only. The final interesting architecture we discuss is attention. The attention mechanism allows a network to focus on the most interesting values of an input set. If a certain interesting key is present in the data, the network returns a value according to a learned key value lookup. Attention is a popular mechanism, and for example used in natural language processing transformers in the form of self-attention. The last video of this chapter discusses reinforcement learning. In reinforcement learning, we not only want to compute a single function, but we want to learn a whole sequence of decisions. An agent repeatedly is presented with a changing environment, which is modeled as a Markov decision process. The agent then has to choose an action, hopefully maximizing its total reward over time. Sometimes the environment is too large to learn. In this case, reinforcement learning uses a neural network to approximate the current state of the environment. Thanks for watching this video.